So my name is Ashish, and I'll be talking a little bit about artificial intelligence. It's the big thing these days, the buzzword that everyone uses. And so I thought maybe I'll share a little bit of what is artificial intelligence, how long has it existed, and if you were to, for example, join college and start take a course on AI, what is it that you expect to learn? Okay, so the first slide is about myself. As I have a bachelor's in computer science from IIT Kanpur. I have a PhD in computer science from Stony Brook. Um, and my thesis topic was something also on artificial intelligence. It's one form of artificial intelligence, and we'll talk about it in a little bit. After I completed my PhD, I joined a nonprofit research lab called SRI International. It's right next to Stanford University in Menlo Park. And over there, I worked on a bunch of things, which again can be loosely classified as AI. Um, for the last 6 years, I've been at Microsoft, again working on AI related technologies, GPT and Copilot and stuff. Okay, so I'm a researcher by heart, so I have a lot of research publications. So I'm more than happy to talk about my own research. But over today, I'll just sort of focus on what is AI. So, before we get started, here's a warm up exercise. Uh, which of the following four things that you see, A, B, C, and D, use AI or have artificial intelligence built in? So, Rishi, did you want to do a poll? Okay. Is there a way we can see on live how many people are answering what? Rishi, should I
Yeah,
just continue?
I think it's on the stage right now.
Oh, the poll results are there. I, s- oh, okay, I can see the poll. I see. Okay, I did my vote. Okay. Anyway, so the results will be shown after the poll has ended. So should I just continue, Rishi?
Yeah.
Yeah. Okay. So this was a trick question. There's no right answer because all of those four things have AI. So AI is actually some form of a catch-all term, and there's no crisp definition of what is AI, what is not. But roughly, any computer program and an automated tool that exhibits human-like intelligence is is termed AI. So a computer program that can play chess with you because it like seems like a human is playing, it sort of involves some intelligence to play the right moves. That classifies as AI. A program that, for example, solves a puzzle like Sudoku might also appear as possessing human-like intelligence. Chatbots, ChatGPT, you can converse with ChatGPT, and again, it sort of feels like you're talking to a person. Not exactly, but at least in some in some form. Voice assistants, robots, they all have some kind of intelligence, and so roughly you can call them um, as having AI or using AI. But we see all these different applications of AI, but is it all the same or are there any differences? So it's like a catch-all thing. It seems like everything is AI. So what is not AI, right? You might wonder. Um, so there is, so you might think that maybe there is one algorithmic concept or computational method, which if you use, then you sort of develop all these AI systems using that. But the reality is that there's no single technology, and AI actually is a catch-all term, as I said, for a lot of different techniques that were developed in computer science over the years. And um, before I go to some of the similarities, there's another trick question that I can ask here, which is if I were to give you, let's say, two choices, let's say artificial intelligence, and I ask you which came first. Did AI come first, or did, let's say, Windows operating system? Did it come first? So, what would you think? So, again, I'll just give a couple of seconds for you to think about it, of what you think came first. And it'll turn out that the thing is that AI, the term artificial intelligence, was coined as early as 1956. So, almost like as people were developing these machines with more and more powerful machines, the first application that people were thinking about it was to build a machine that has human like intelligence. And so initially, actually, a lot of computer science was just AI, because that was the goal of building a computational machine, to sort of eventually make a machine that has a little bit of human like intelligence. Um, so So as I said, AI is roughly defined as something that gives impression of possessing some human-like intelligence. Um, uh, so if the definition is so general, then you would wonder, what would I really learn if I were to take a course on computers, or on AI? And there are a lot of foundational techniques, and there's not one, but actually a very wide variety of techniques that you would probably learn if you were to do a course, or do a graduation, or do a bachelor's degree in topics related to AI. And I'll roughly try to illustrate some of them. So one thing that you must be hearing a lot these days is deep learning, right? So of course, deep learning is now the the most basic and central thing in AI. Um, uh, And in fact, if you think about it, as I said, there are a lot of foundational concepts using which people build intelligent systems. And neural networks is one such concept. And deep learning is a gradual progression of taking a small neural network and making it larger, 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 with small tweaks, um, so that they can sort of, you can train them uh, to do any task. And in fact, what we have seen, so originally, maybe even 10 years back, people thought that you have to train a network for doing one task, right? Maybe speech. So there'll be one network that does speech, one network that answers questions, one network that answers maybe chemistry questions, one network that answers math questions. But what has happened in the last 3 or 4 years is, with this chat GPT and GPT, they figured out that if you really build a network which is really large enough, uh, then it has this properties of emergent behavior, although they're not trained for answering math questions or for answering chemistry questions. These networks can actually answer them. So these are, in some sense, emergent properties of these large, uh, what are called language models. And we can sort of discuss that more if people are curious about how language models work. Um, but definitely AI is not just deep learning. And if you so deep learning, as I said, is one very promising and a technique that has had a lot of impact in the last 3 years. But if you go one step above, deep learning is actually an instance of a machine learning technique. And again, machine learning is a broader umbrella which has deep learning, but it has a lot of other models. So not just neural network based models, but decision trees, or other forms of linear models, non-linear models, that you can also learn. And all those constitute machine learning. And machine learning itself is one part of AI. So AI is this root node under which machine learning is one part. You might be wondering, what is the other part? And within machine learning, deep learning is one part. And again, you might be wondering, what are the other parts in machine learning which are not deep learning? And as I said, they're linear regressions, uh, decision trees, and so on. And we can sort of discuss all of them as well. But to concretize things so that these things are not very abstract and you get a very clear idea, let me do a very quick thing that I did last night, which I think will help you to actually see the differences between all these different forms of AI. So what I'll do is I'll share my screen. I'll stop sharing the presentation itself and go to sharing my screen. So let me just share my entire screen. Um, I have two, so I'll select this one. Okay, so you must be seeing my screen now. Yep. So, so you have you? How many of you have heard of the Tower of Hanoi problem? So, which is actually in my screen. Let me open a tab, um, browser, and so have you heard of this puzzle, Towers of Hanoi? Right? I'm sure some of you have. Uh, and the puzzle is as follows. What's a good picture? Something like this, right? So you are given uh, a peg and some uh, things that sit on it, right? You have to stack them up, and these things are all of different sizes. You have to stack them up so that the only rule is that you can only a small piece can go over a bigger piece. You cannot have a bigger piece go over a small piece. Yeah. So and the task is to move one of these pyramids over here to, let's say, uh, on this on the goal peg. Yeah, and you can only move one at a time, with the rule that you cannot put a big one over a small one. You can only put a small one over a big one. Yeah, and so that's the puzzle. So if I want to solve this puzzle, right, one way is, uh, let me uh, one way is let's see if this works out. I just encode the rules of what is allowed and what is not allowed into in and give it and tell that to the computer, right? So over here, um, I'm sort of um tell me if you're not following or if this is too abstract or uh, but let me try. So I'm going to encode that puzzle, the Towers of Hanoi thing, and just encode the rules of the puzzle of what is allowed. I'm not going to encode the solution. Okay. I don't know what the solution is, but I know what the rules are, right? So here you would see that I have encoded a rule that you can, for example, there are three towers, right? One, two, and three. If I have, so I'm reading this first rule over here. Let me highlight it. You can forget the last part over here. What the first rule says is that if you have X at the top of the middle tower, you can pick it up, and and if the first tower is empty, then you can put the X peg on this first tower, and then the middle tower will not have X anymore. It will have whatever remains, which is Z over here. And the third tower doesn't change. The third tower was W before, and it's W after. Yeah. So this is just one rule, right? You can sort of take a top peg and put it on an empty tower. Similarly, if the first tower has already has something like Y sitting on it, right? Then you can put a X again from the X was sitting on the second tower. I can pick up the X and put it over the Y on the first tower, and I'll get X, Y, and whatever was on the first tower before. The middle tower now becomes Z because I took X away, right? And the third tower remains unchanged, right? But there's a condition, right? That the since there was already Y on the first tower and I'm putting X over it, X has to be smaller than Y. So I just say the condition that X should be smaller than Y. So my towers, I'm sort of representing them as a list of numbers, right? And I'm sort of taking, you can take a number from one tower and put it on the other tower as long as the top thing in the tower is bigger than this number. So this is the rule of the game. This is not a solution, but this is a rule. And this rule, there are like 6 instances of this because you can pick. a different source tower and a different target tower, right? So there are like six instances of whether you're moving from 3 to 1, 3 to 2, 2 to 1, 2 to 3, or from 1 to 2 and 1 to 3. So this is this simple set of rules capture the rules of the Tower of Hanoi game, and then I say that initially the starting state is that I have, and the third tower I have these three pegs, 1, 2, and 3, and I can say my target is. So let me first load up this program. So my target is that I want uh, 1, 2, 3 in the first peg, right? And I want the second one to be empty, and I want the third one to be empty. So if you see carefully, nowhere I have actually told the computer how to solve this program. All I've encoded in the computer is the rules of the game, right? And then I do this, and the computer comes back and says yes. And yes means that it was able to find a way to move those three pegs, the three pieces into the onto the first tower from the third. Okay, and it sort of did a little bit of search. So I had this uh, print statements over here, which are kind of showing what all it tried. So in the end, it found a way, but it tried a bunch of things in between. And you can see that all of the intermediate states, it has the condition is satisfied that there's always a smaller number before a bigger number. It's never the case that you have 3 followed by 2, because of course we sort of explicitly mentioned that that's the rule that you have to follow. You can ask, well, if I give something which is impossible, uh, like let's say 2, 1, 3, right? That's not possible. It should ideally come back and say that this is. It should come back and say or no. Um, yeah, says that's not possible. So, so this what I just showed is symbolic AI. And what I mean by symbolic AI is that this is not machine learning. It's not deep learning. It's another form of AI which is not machine learning. And what this other form of AI is doing is it is representing the problem, yeah, symbolically in terms of rules, and it has a way of reasoning about rules. And it just did those that, and this program that you see over here is called, it's a Prolog program. So the language is called Prolog. It's a logic programming language. Um, it's named logic programming because you can write logical statements and it'll do the inference itself. And the way it does inference is basically symbolic AI. It's reasoning with uh, with logic and with rules rather than with numbers that neural networks reason with. Okay, so let's go back to the presentation. So I stop sharing this one. I start sharing my presentation again. Um, yeah, we are like almost, the first session is going to end in 4 minutes, but I think I'm quite a bit there. Um, so we did this, so we did deep learning. Um, yeah, so this is what I was illustrating. What is AI beyond machine learning and deep learning? Um, Machine learning is when you learn a computer program to reason like humans based on data. So you take all the data that humans have generated, for example, and then you teach a model to sort of mimic that. So in our Towers of Hanoi problem, if I asked Rishi to solve that problem and I asked each one of you to solve that problem, and you all gave me a solution, I took all that solution data and then I could create a neural network to sort of memorize or sort of learn patterns and figure out exactly what the rules are. That would that would be called machine learning or deep learning, right? Because I trained a neural network based on the data that you generated. Symbolic AI, on the other hand, the way I showed, is there's no data involved. I didn't ask you all to solve the problem. I didn't even show it one example solution. I just told it the rules. I just gave the rules of the game and it figured out just by trying out all the rules, which ones worked, which one did not work, and backtracking and figuring out the sequence that works. So that's symbolic AI versus machine learning on the Towers of Hanoi. Now there's another interesting part of machine deep learning, which is reinforcement learning. So the difference between reinforcement learning and something like deep learning or supervised learning, in which Rishi and each one of you gave me data of how you solve the problem, and I use that to train my machine. So in reinforcement learning, I don't use training data like the ones you generated. What I'll do is I'll just give a reward to the to my model. If the model takes a step that, for example, violates a rule, I will give it a punishment. I'll say, oh, this is a bad choice. And if it does a good step, which leads to a desired state, then I'll give it a reward. And then again, you can train machine learning models that way. That thing is called reinforcement learning. And of course, these techniques may or may not work on a given problem. Um, so yeah, so machine learning, what is machine learning, which is not deep learning? Things like linear regression that you probably studied in high school. You're given a bunch of points, you try to find the best line, and you use that line to make predictions or extrapolations from data. That's machine learning, but it's not deep learning because you're not training a neural network, you're training a linear model. Okay, um, I have a couple of more slides. Um, so we can do another poll. Uh, we are going to run out of time. Rishi, would it just cut us off, or would it let us continue?
I think there's around 5 more minutes left.
Okay, cool. So here's a poll. Which of the following is symbolic AI, or which of these things use symbolic AI and not machine learning or deep learning? And the options are there's a car autopilot, there's chat GPT, there are stock market predictors, and a chess playing robot. And again, you can go to polls, um, and you can sort of pick your answer. Has everyone picked their answers? Oh, did my answer already show on the screen? so you can see whether you got the right answer or not. It's oh yeah, the screen shows it. Yeah, a chess playing robot actually just works off rules. It is not trained on, for example, solutions that people have done, or you just tell it the chess rules and it sort of figures out by looking ahead which move would be the best. Of course, these days people are the latest in research is that you don't want completely symbolic, you don't want a completely neural solution, and people are looking at neurosymbolic AI, which is AI which has some parts of it is symbolic, reasons with rules, and some parts of it is learning from data, and that's very powerful as well. Chat GPT is purely neural. Stock market predictors can be both. Uh, I don't know what they're using right now. I'm not in that part of the world. Car autopilot is mostly again neural because they are processing feed from your lidar, from your camera, and then taking those images and figuring out objects. And all those are better done with large neural models. Okay. Yeah, so I already did this. I sort of gave you a flavor of what is symbolic AI through this Towers of Hanoi thing. But there are several things. Like, of course, we mentioned chess bots, but there was a field called expert systems, which was very popular before machine learning took over the world. SAT solvers do exist, and people still use SAT solvers. These are again a very classical example of symbolic AI. All of logic and logic programming that I showed is symbolic AI. You have some computer algebra tools, which are also symbolic AI. Computer algebra tools basically do algebra for you, and they don't do it numerically. Like your graphing calculator, most of your operations on your calculator are numeric, right? They'll integrate, but they'll integrate by sort of summing, doing a summation. But computer algebra would actually integrate it symbolically or differentiate things symbolically. And again, you can do that. And that's what computer algebra systems are. Again, That's an example of symbolic AI. So I think that was the content that I have or I had. But I think what I was looking forward to is if there are questions that people want to ask and details that they want more on any of these topics. Yeah, so this, I see a question on the chat. Uh, so is neuro-symbolic AI similar to synthesis by which the creator defines boundaries, rules, and then the program is adaptive and can learn how to most efficiently work? So, so the neuro-symbolic field uh, is very cutting edge in the sense that people are defining what neurosymbolic is even today, right? So there's no standard neurosymbolic thing technique, but people are thinking of different combinations. And one of the combinations they're thinking is along the lines of what you're suggesting is uh, is that you define some rules and then you have training data and you train your machine learning model, but you train the machine learning model in such a way that it does not violate the rules. And the rules are hard, right? They're hard constraints. So currently, if you just think of machine learning or neural networks, they don't have a notion of hard constraints. You can give them data, they learn, but what they learn may violate some of your basic tenets or basic rules that you have. And there's no guarantee or there's no effective way people know of how we can at the same time learn and also enforce these hard constraints. Um, I mean, people know a little bit, right? It's one of those research problems that people have worked on. There are other ways of doing neurosymbolic, which is you do like part of the solution neural and the second part symbolic, or you do some part of the solution symbolic, or you actually compute the features symbolically, and then you learn a neural model over those features. So so as I said, there are a lot of different ways in which people are thinking about how can I take a big problem, partition it into pieces that are best suited for symbolic AI, other pieces that are best suited for neural or machine learning or deep learning, and then create a solution um, which is the best, right? Gets the best of both worlds. So there are people in my team also who work on neurosymbolic. There are a lot of researchers in MIT, um, Pennsylvania, Texas, Austin, uh, yeah, who are deeply interested in working on this on neurosymbolic AI. Is the machine able to judge what would be a rule or not, given a training set for data A, then get data B without training, and it knows how to operate with inferred boundaries? Yeah, so rule inference is a very interesting topic in AI. If you think about it, the way deep learning and neural networks work is that actually they are just number crunching machines, right? They are just memorizing things and crunching numbers. So they look for some patterns and use those patterns to make predictions. But what patterns they have learned is kind of hidden. Um, So they may be learning some rules, but we don't know what rules they have learned, and it's difficult to extract those rules out of the model once you have trained the model. There are other methods in machine learning, like decision trees, in which you explicitly try to learn rules. So you say that I want to learn a rule that will do this prediction, and for some of those methods, you can actually from data learn rules. Once you have learned those rules, then you can sort of use them in the future, just like you're suggesting. So again, there are different techniques in machine learning and even symbolic AI in which you can sort of learn rules and then exploit them later on for some other tasks. So what are the limitations of symbolic AI? That's a very good question. Um, so one thing with symbolic AI is scalability. That is, what it is doing underneath is it's trying to take all the rules that you've given it, and it's just sort of applying all of them and trying to see if I can find a path to the solution from the source, um, by basically just trying everything out, right? So if you have too many rules, if you have too many entities, scalability is a big challenge for symbolic AI. You can solve small problems, but once the problems become large, uh, symbolic AI starts having a little difficulty. It'll come back, but it'll come back maybe in an hour with an answer. Sometimes it may not come back because ultimately these problems that symbolic AI or actually any logic, I don't know if you, well, probably you are a high school student, so you don't know. There is in computer science, there are notions of what is computable, that is what are the class of problems for which a computer can that can be solved using a computer, like with an algorithm. But there are also problems which are unsolvable in a very formal way. There's a precise notion of unsolvability. And the challenge with AI in general is that even most basic logics are undecidable, which means that these computer programs can sort of go into an unending search and not never come back with an answer. And that's one challenge with symbolic AI. Most of the problems are undecidable, which means that you can always give it an instance on which it'll just keep churning the wheels and never come back. So scalability is a big challenge. Um, but on the other hand, neural networks also they can scale, um, uh, thanks to all hardware, GPUs, and efficient methods for training these large things. But you see that they can only accept certain inputs. So, for example, a neural network, even ChatGPT for that matter, cannot really add two big numbers, right? If you give it like a 15-digit number and ask it to add if you ask it to add two 15-digit numbers, it'll probably come back with the wrong answer. Okay, so there's one more question. So this is similar to the rule learning from data, right? If you have a bunch of data on a lot of humans, and you sort of notice that in all that data, people always washing hands before eating, washing hands before eating. Um, you can sort of learn a rule, right? That uh, one always washes hands before eating, because all your data is consistent with that. All your observations in your data are consistent with that rule. Um, this thing is done, as I said, it is more done in symbolic AI. Uh, and with neural models and deep learning, you hope that it's implicitly learning those rules somewhere in some representation, but you never know for sure that it has learned that rule. In symbolic AI, you actually explicitly try to learn a rule from data, just like you're suggesting. In fact, our team has a product called Flash Fill in Excel, in which if you have a Excel spreadsheet, you have some data and you're creating a new column. Let's say you have uh, a classic example is first name, last name. You have Ashish Tiwari in one of the columns, and you're, let's say, just generating initials, AT. So you give one example, AT, and you have, let's say, Rishi Vora, and you write RV because those are the initials, right? And then let's say you have another 20 more names. What Flashfill does for you is once it sees these two examples, or just in one example, it's able to figure out a pattern, a rule, of how you're generating this data, RV from Rishi Vora. How did you generate AT from Ashish Tiwari? And it's able to learn that rule, and that's what we do. We learn that rule, and then we apply that rule to all other rows, and we're able to fill the row for you. So this is a feature called Flashfill. Again, it's based on symbolic AI. We explicitly learn the rule. And we have a similar thing that also works on Visual Studio developer tool. If you're editing code, and if you do two edits which are very similar, then we sort of figure out a general rule. Oh, what you're trying to do is apply this rule, and then we say, oh, there are 50 other places in your code where you can apply the same rule, and do you want me to do that? and then you say yes, and then we apply that same rule 50 other places, and you're able to sort of consistently edit your code or refactor your code. Again, they're both these things are based on symbolic AI. Okay, so can you discuss what your PhD project was about? Um, so, so my PhD project was about SAT and SMT solvers. So, uh, let's see. Um, so there's a field called mathematical logic, yeah, and you like I maybe I don't know if you've learned Boolean algebra in your math classes, uh, but uh, there's a logic called propositional logic in which you talk about Boolean variables, true, false, right? And you talk about Boolean operators, how you can combine these true and false values using and, or. So true and true is true, true and false is false. So you have these rules, right? You have like these equations or these algebra about Boolean values. That's why it's called Boolean algebra. And you can have a logic over it, uh, which is like trying to give all the rules that will generate true Boolean formulas given all true Boolean formulas, right? So um, it's called propositional logic, and you have variables, right? You say x or y, so either x is true or y is true. Then you can say, oh, but I also know that x or z. So either x is true or z is true. So I know this other fact. Maybe I know other fact that not x or not z, which is so either x is false or z is false. And you can write um, these constraints, Boolean constraints, and then you can ask, is a big constraint satisfiable or not? Is there a solution for this problem? Um, can I make it all true by setting values for x and y and z? So that's called satisfiability checking, or uh, determining satisfiability of a formula. So there are SAT solvers which will do that. And similarly, there are more richer logics than just Boolean logic. And then you can ask the same question: if I give you a formula in that logic, can you tell me if it is satisfiable or it is not satisfiable? Can I instantiate the variables? It's like in your math thing, right? You say x equals 5, yeah? That's satisfiable because you give a value of 5 to x and then it becomes 5 equals 5, which is true. If I say x square equals minus 1, uh, that's an unsatisfiable formula, unsatisfiable over over the domain of reals, because if you have reals, then x square can never be negative. So it's an unsatisfiable formula in some logic, right? So there are lots of different logics. And then I can ask the same question. I'll give you a formula in that logic and you tell me whether it's satisfiable or not. And my PhD thesis was about giving algorithms for deciding satisfiability of formulas in certain different logics. So roughly, I hope it made sense. But it was symbolic AI, in the space of symbolic AI. How do Tesla's systems work so fast to interpret data? Yeah, um, well, I don't think I know for sure. I can only make guesses, but so maybe I'll abstain from answering that question because I don't have any definitive answer. Uh, it's a good question. Um, how fast? So it all depends on the size of the model, and and how much compute you have, right? So if you just have the right size model and you have the right GPUs, the right hardware, then actually making inference is very fast. Um, that's all I can say. So you just have to optimize the hardware and the software layer, just have the right size model and just the right hardware so that you in one go are able to sort of in parallel take all that data, process it, and create a generate a um, generate a prediction for the next action. I can say how we or people in my team use AI. I already gave you a couple of examples of symbolic AI that we've developed and that we've put in products. And we are doing similar things even now. So we are trying to put in more symbolic, neuro-symbolic techniques. Uh, Most of the time, we focus on neuro-symbolic or symbolic because of predictability. With symbolic techniques, you know exactly every time you do the same action, you'll get the same result. With neural, it's stochastic. Um, st- uh, if you carefully design symbolic techniques, then they are also fast. You can make them reasonably fast, reasonably accurate, and predictable. So those are the benefits of symbolic, and that's why we sort of tend to use more symbolic. Um, uh, what else can I say? But of course, Microsoft is also big on the neural sides of thing. We already know about the OpenAI models, and you might have heard Satya and other people say that one of the big things is how we can use these large language models to build features that will make people more productive, and they won't have to, for example, go to a Google search or go outside the app or the thing they're working on. Suppose you're working on a Word document and you're sort of stuck. Can I sort of very quickly help you right there using ChatGPT? Because I also have knowledge of the Word document that you're working on. So I have the context of what you've been doing and what you're trying to do. And maybe I'll be able to use that information along with a model like ChatGPT to best give you a response or unblock you on whatever you're trying to do. And same for example, if you're working on a spreadsheet, if you're working on PowerPoint, um, can we use ChatGPT or these GPT class of models to help you in the thing that you're doing, uh, even if you're not an expert. So you're not an expert in Excel spreadsheets, but you want to create a pivot table. You don't know how to do it. Rather than going on web and searching for how to and seeing YouTube videos on how to do it, maybe you can just say what you want to do, and then we'll try to use GPT, use the context or the data that you have, and try to figure out, oh, this is what you want to do. This is the most likely thing that you want to do, and we'll make that prediction.